Welcome students. In last class we have derived the Bernoulli equation or a mechanical energy balance equation to calculate the power requirement of a hydraulic system. Now in this class we will discuss in detail about the friction losses in the hydraulic system. So how to calculate this sigma f term. So what is the mechanical balance term? 1 by 2 alpha V2 average square minus V1 average square plus 2 Z2 minus Z1 plus P2 minus P1 by rho plus sigma F plus Ws equal to 0, where V2 1 and 2 are the two given point in the system. One is the entry point in the system, 2 is the exit point of the system. So here we are doing the mechanical energy balance of the overall system, and this is the kinetic energy term, this is the potential energy term, this is the pressure term, this is the losses due to the friction, this is the power of the pump or the turbine. So this is in this equation this is positive when the work done by the system, and this is negative when the work done on the system. Okay, if this sign is negative then it will be opposite. So you have to careful about the sign of the pump. Now we will discuss about the F. F is the different friction losses from the system. So what are the friction losses in this hydraulic system? So first, a friction loss we have already discussed with you during the derivation of pipe flow problem, that is the friction loss due to the solid boundaries. So that is called the film friction or the major friction loss. So what is the friction, that friction? So for that we have derived the friction factor. So what is the friction factor? Friction factor is the ratio of the shear stress term at the wall to the kinetic energy head, that is 1 by 2 rho v square average. So friction factor is defined as tau w upon 1 by 2 rho v square average. So rho average square, rho v average square. So basically this is the kinetic energy term, this is the friction term, means shear stress term at the wall. So generally we solve the problem for the tubes. So we will define f value of friction factor for tube first. So for tubes, and if the flow is laminar, then the Vz equal to Vz max 1 minus rho r square by capital R square, where capital R square is the velocity. This equation we have developed during the derivation of Huygens-Pauli equation, which is the equation represent the mass flow rate in the circular tubes. So from V we can calculate the Vz equal to, then what is the value of Vz? Vz equal to 2 mu Vz max r, where Vz max is the maximum velocity which occurs at the center of the pipe. When you substitute all the values, you will get P naught minus PL by 2L r. So this equation we had already developed during the pipe flow problem, which I have discussed before mid semester. So you can refer the notes before which I have given to you before mid semester for derivation of this equation. So when you substitute the value of tau w in the original equation, this equation, you will get the value of friction factor. So friction factor will become 8 mu by rho r v average. So where r rho r v by mu. So then if you multiply r with 2, it will become d. So rho dv by mu, that is the Reynolds number. So then friction factor can be written as 16 by r nre or re. Re is the Reynolds number. So here friction factor can be written 16 by re. This is for the laminar flow, because this equation which we have used to calculate the friction factor, Vz equal to Vz max 1 minus r square by r square, this equation is only true for the laminar flow. If flow is turbulent, then friction factor will depend upon the smoothness of pipe as well as the flow rate or the Reynolds number. So if flow is turbulent, then we can use the Moody's chart. So this is the Moody's chart. Here we define a roughness factor, that is the z by theta, xi by d. So d is the diameter of pipe, xi is the thickness of the roughness. So thickness of the roughness is the thickness of the this point here to here, that is the thickness of the roughness. So if you know the value of xi and you know the value of d, you can calculate the friction, you can calculate the roughness factor. If you know the roughness factor and if you know the Reynolds number, you can calculate the friction factor. So now I am coming on the McCabe-Smith book. This is the 5th chapter of the McCabe-Smith book. So this part, this I have already discussed you before the mid semester, how to calculate the friction factor using the in the laminar flow region. That is, in the laminar flow region you can calculate by 16 by NRE. NRE is the Reynolds number, and if you, the flow is turbulent, then you can use the Moody's chart. So in the Moody chart you have the you have to calculate the first the roughness factor, that is the xi by d, and then you have to calculate the Reynolds number, and by using the these two you can calculate the friction factor. Now this is from the same topic in the McCabe-Smith book, which is 5th chapter of the McCabe-Smith book, unit operations. Now you can see here, this is the xi. In this book it is represented by k. So k is the thickness of the roughness of the pipe. So as the value of d increases, your friction factor will reduce. So this is the Moody chart given in the McCabe-Smith book. So if you know the value of k by d or xi by d, and you do know the value of Reynolds number NRE, you can calculate the friction factor. Values of k by d is also given for the this different pipes here. For cast iron pipe, value of k is this, for because the roughness of the material surface will depend upon the material. So based on the different material, you have the different value of the different values of the xi or the roughness. So when you divide roughness by area, you can calculate the roughness factor. Now there are some formulas, empirical formulas also, which can use to calculate the friction factor for a given system. So these are the formula 5.46, 5.47. These are the empirical formula which directly correlate the friction factor to the Reynolds number. If you don't want to use the Moody's chart, then you can use this type of formula. These formulas are generally given in the chemical engineering handbooks. So these are the empirical formulas. There are no theory behind these formulas. Different people has done the experiment and calculate the at the different Reynolds number and calculate the friction factor experimentally, and then they fit the data in the equations, and they will get these type of correlations. So these are the empirical formulas. So you can either use the Moody chart to calculate the friction factor in turbulent flow, or use the empirical formulas to calculate the friction factor. Similar type of formulas are also given for the non-Newtonian fluids. These are the formulas for calculating the friction factor for non-Newtonian fluids. These formulas are for calculating the friction factor for Newtonian fluids, and these formulas are for calculating the friction factor for non-Newtonian fluids. So here also for laminar flow, it is calculated as F equal to 16 bar NRI, and N is represented for the non-Newtonian fluid, and N can be calculated by this Reynolds number can be calculated by this formula, where this N is the this is the factor used in the power law. So if you remember the power law, in the power law you have the shear rate to the power N. So this is the same N. So value of N is 1 for the Newtonian fluid, and it may take the different values for the different types of fluids. For pseudoplastic fluid, it should be less than 1, and for the dilatant fluid, it should be the greater than 1. So this is the similar Moody's type of chart for non-Newtonian fluid for calculating the friction factor. Now suppose you have the system where the temperature is changing with the along the length of the pipe. If temperature is changing, then you have to divide the friction factor with a factor that is represented by this here. So you have to divide the friction factor with a factor which is basically the ratio of the viscosity at the wall and at the bulk. So this is mu is the mean velocity viscosity of the fluid at the mean bulk temperature, and mu w is the viscosity of viscosity at the temperature of the var of the conduct. So if you have the different if you are increasing the temperature or decreasing the temperature, you have to divide the friction factor with this factor. For this is for the actually this is given wrong here. This is for the when you have the laminar flow, and this equation is for when you have the turbulent flow. Okay, so that this should be greater than 2000. This should be less than 2000. This should be greater than 2000. These two equation can be used when you have the laminar flow, and these two equation can be used when you have the turbulent flow. Now suppose you have the a closed channel which is non-circular, means you have the pipe which has the non-circular cross section. So in this case you have to define a new parameter that is called the hydraulic radius. So here RH is represented the hydraulic radius. So hydraulic radius equal to S by LP. S is the cross-sectional area of the channel and LP is the parameter of the channel, or the wetted parameter, means the parameter of the channel which is in contact with the fluid. So you have to calculate the RH, and suppose the fluid is circular, then RH is equal to pi d square by 4. Surface area, cross-sectional area of the circular pipe is the pi d square by 4, and the parameter of the circular pipe is the pi d. So if you divide it, it will come the d by 4. So d by 4 is the hydraulic radius of the circular channel. So this hydraulic radius is used when you have the non-circular channel for calculating the friction factor. So suppose you have the non-circular channel, suppose you have the endless channel. Endless means you have the two concentric pipe and fluid is flowing between the two concentric pipe. So for this case you have a suppose outer diameter is d0 and inner diameter is di, and between d0 and di fluid is flowing. So pi d0 square by 4 minus pi di square by 4, this is the cross-sectional area of the flowing channel, and the pi di plus pi d0 is the cross-sectional area of the is the parameter of the flowing channel. So you will get d0 minus di by 4. This is the hydraulic radius of the endless. So similarly you can calculate the hydraulic radius of the cubical channel or different type of channels, and rectangular channels and square channels. Okay, so you can calculate different type of, like for squared duct with the width b, you have the hydraulic radius b. Okay, so once you know the hydraulic radius, you have to just replace the d in the original equation to 4h or r to the 2h. So when you replace that, you can get this formula for the friction factor, and Reynolds number will become the 4RH V rho by mu. In the original equation it is the d V rho by mu. Here it will become 4RH V rho by mu. You have to calculate the same method. You have to use the same method to calculate the Reynolds number. Once you know the Reynolds number for laminar flow, then the friction factor equal to 16 by NRE multiplied by phi A, where phi is the function of di and d0. So this is the phi A. So you can calculate the phi A from this graph, and then you can substitute the value of phi here and calculate the friction factor for laminar flow. Similarly, you can calculate the friction factor if the flow is turbulent, okay, in the same manner by using the Moody's curve. When you use the Moody's curve, then you have to take care that whenever the d comes, you have to replace the d to the 4RH. Okay, so when you calculate the surface friction factor, okay, when you calculate this value, K by D, okay, roughness factor, when you calculate the roughness factor, so this D will be replaced by the 4RH. So here it will come K by 4RH, and Reynolds number will be calculated by the new formula as I mentioned here. Okay, so Reynolds number, in Reynolds number D will be replaced by the 4RH. So Reynolds number is, for circular tube, Reynolds number is dV rho by mu. In the non-circular tube ducts or cross channels, Reynolds number equal to 4RH V rho by mu. So calculate the Reynolds number by 4RH V rho by mu. Calculate the surface factor by roughness factor by 4RH divided by K divided by 4RH, and then calculate the friction factor by using the Moody chart, by same Moody chart. Okay, so this is the calculation of the friction factor when you have the flow through non-circular cross sections. Now this is about the friction factor. So this is the friction loss due to the, this is the friction loss due to the, when you have the due to the solid wall or the solid channel. Okay, so due to the friction of the solid wall. So this is the losses. F can be calculated then. F equal to L by RH or L by D. It should be the 4RH. So L by delta L by D V square by 2. Okay, so here you substitute the value of F, then you substitute the delta L. Delta is the length of the pipe, divide by diameter, multiply by V square by 2. Then you will calculate the friction loss. So I will again discuss it detail whenever we calculate the total friction loss. Now there are friction losses due to the, when the flow is changing, the direction of flow is changing, or the velocity of the flow is changing inside the tube. So why the direction will change? Suppose you have a bend in the pipe, so that due to that bend the direction of the flow will change. So due to the change of the direction, you have the loss of the mechanical energy. That is the that is called the change of the, that is the loss of the energy due to the change of direction. Similarly, if you change the diameter of the cross sectional area of the pipe, suppose you have a pipe which has the 2-inch diameter, again then you add a pipe which has the 1-inch diameter, so you are reducing the diameter of the pipe. When you reduce the diameter of pipe, there is a sudden contraction. So due to that contraction, you have the energy loss, mechanical energy loss. Similarly, if you have the expansion, suppose you are using a pipe, 1-inch pipe, and then you add a pipe of 2-inch, then you have the sudden expansion. So you can you may lose the energy due to the sudden expansion. So due to the sudden contraction or sudden expansion, you may lose the energy, and you may lose the energy due to the change of direction, due to the elbows, 90-degree elbows or 180-degree elbows. You may also lose the energy due to some other fittings like walls. Due to the different type of walls, you may lose the energy. So these are the losses which is occurred due to the fittings or due to the different type of fittings used in the system. So the friction loss due to the loss of energy due to the friction of the pipe is called the major loss or the skin loss, and friction, the losses due to the fittings or the different type of fittings or the due to the contraction or bends are called the, or due to the different type of walls, these type of losses are called the minor losses. So here we have the minor losses and here we have the major losses or the friction losses or the skin losses. So minor losses are due to the walls, bands, fittings, and the major losses is due to the solid wall of the flowing channel, like the solid wall of the tube. Okay, so now we will see how to calculate the minor losses. Suppose you have this type of channel. Here fluid is entering from a the fluid is flowing in a pipe. Suddenly you increase the diameter of the pipe. So here the pipe is diameter is less, here pipe diameter is more. So due to the change of the diameter of pipe, this is called a sudden expansion. The sum of the energy will, mechanical energy will convert in the thermal energy. Why? Because you have the eddies formation in these corners. So due to that you have the energy loss. So this energy loss can be calculated by this formula. This is the energy loss or friction loss, that is equal to Ke V square by 2Gc, where Ke is the called the expansion loss coefficient. Okay, so Ke is the expansion loss coefficient. So how to calculate the Ke? This is the small derivation to calculate the Ke. You can check this derivation. I am only giving you the final answer. Final answer is the Ke equal to 1 minus Sa by Sb square. Okay, so what is the Sa and what is the Sb? Sa is the cross sectional area at this point at the upstream channel, and Sb is the cross sectional area at the downstream channel. Upstream channel is called the channel from where the fluid is entering, and the downstream channel is called the channel where the fluid is leaving. So Sa is the cross sectional area at the upstream channel, and Sb is the cross sectional area at the downstream channel. So this is the friction loss due to the sudden expansion, can be calculated by this formula. HFE equal to Ke V square by 2Gc. Gc used when you are using the British unit. If you are using the SI unit, then this Gc will remove. Okay, you have to remember this is not G, this is not gravity, this is the Gc. This coefficient will come when you are solving the problem in the British unit. If you are solving the problem in the SI unit, then this Gc will not come. Okay, so the equation will become the where K is the expansion loss coefficient, and the Ke can be calculated by 1 minus Sa by Sb, where Sa is the diameter of the upper stream or surface area of the upper stream channel, and Sb is the surface area of downward stream channel. Similarly, if you have the sudden contraction, so sudden contraction means, suppose you have this type of channel where you have the large diameter pipe which is situated before a small diameter pipe. So here the flow will increase, and due to here there is some disturbance in the flow, and due to this disturbance you will lose some of the mechanical energy. So how to calculate this loss of the mechanical energy? That can be calculated by this formula, where KHFC is the loss of the energy due to the sudden contraction, which is equal to Kc Vb square by 2Gc. Here again Gc is not the gravity, it is the coefficient which comes in the as a British unit. If you are using the SI unit, this Gc will not come. So for SI unit, this equation will be HFC equal to Kc multiplied by Vb square by 2. Okay, so make sure, be careful, this Gc will come only in British unit, this Gc will not come in the SI unit. In SI unit the equation will be Kc Vb square by 2, where Kc is again what is the Kc? Kc is again the contraction loss coefficient, and Kc will be calculated by Kc equal to 0.4 multiplied by 1 minus Sb by Sa, where Sa is the upper stream diameter, means diameter of the larger pipe, and Sb is the lower stream diameter, means diameter of the smaller pipe. So Sa is the surface area, it should be surface area, cross sectional area. So SA is the cross sectional area of the this pipe and SB is the cross sectional area of this pipe. So here you have the SB divided by SA. This is the SB divided by SA. So SA is the upper stream and SB is the downward stream. So SA will be greater than SB. This is the SA, this is the SB. SA for upper stream, SB for downward stream. So you will get the 1 minus SB. SB means this value divided by SA. SA means this value. Cross sectional area at this point is SA. Cross sectional area at this point is SB. So this is the formula of Kc. Kc equal to 0.4, 1 minus SB by SA. When you substitute the value of cross sectional area in this equation, you will get the value of Kc. When you will get the value of Kc, you just substitute the value here. You will get the friction loss due to the sudden contraction. Okay. Now you have the friction loss due to the sudden expansion. You have the friction loss due to the sudden contraction. Now the friction loss due to the different type of fittings and walls. Suppose you have the elbow which is used to change the direction of flow, or you have the different type of fittings. So if you have a different type of fittings, you can calculate the friction loss. You can define the friction loss by this formula. HFF is the friction loss due to the different type of fitting, that is equal to Kf VA square by 2GC, where Kf is the loss factor of fitting and VA is the average velocities of the pipe leading of the fitting. Okay, so again you have to make sure in all these equation VA is the velocity of the downward stream. In this equation VA here you have the, in this equation here you have the VB, I think VB. So VB is the velocity at the downward stream after contraction. Similarly in the expansion you have VA. So here VA is the velocity at the before upward stream. So you have to make sure you are using the right value. Okay, you cannot use the wrong value. In the fittings you have the velocity of the downward stream or the average velocity pipe leading to the fitting. Okay, these are the different values of the Kf. So these are the empirical values. Again you have to understand that these values also depends upon the design of the fitting as well as the type of material. So these values are not fixed value. In different books, in different handbooks for different type of materials, you will get the different values. So in a given problem this value will be given to you. Okay, one minute. This VA is the average velocity of velocity which is leading to the fitting. Leading to the fitting means upward stream. I'm sorry, this is not the downward stream, this is for the upward stream. So this VA should be the upward stream velocity, not the downward stream velocity. Okay, and here again you have the different coefficient values for different type of fittings. So for globe wall, a wide opening, it should be 10. For the angle wall, wide open, it should be 5. So you may get the different values of the KF, empirical values from the KF for different type of fittings. For different design of wall it may change, for based on the different type of material it may change. So for different books, like I have the different book here, so here again the values are given differently. So in this book you have the different values, and in this book, this is the McCabe Smith book, here you have the different values. In this is the unit transport phenomena book, here you have the different accomplished by transport phenomena, here you have the different values. So you should make sure you are using the correct value. Okay, so if you add all the equation, V is the average and V is the average velocity, then you will get this equation where this is the HF is the equal to sigma F. So this is the overall losses in the system, in the hydraulic system. So overall losses in the hydraulic system can be written as HF equal to 4F L by D plus Kc plus Ke plus Kf V square by 2. Again this GC is come when you have the British unit. In SI unit the GC will not come. Okay, so this is the equation you can use to calculate the overall friction losses in the system. Again, if you have the different velocity, you have to calculate the value of V individually. If you have the same velocity or throughout the system, you can use a single V average value. Okay, but this is the overall loss or sigma F. Now we will solve some problem related to this unit from the Jinkoblish transport phenomena and unit operation written by Jinkoblish book. So this is also the same friction law, friction factor based on the different value of Kf coefficient, friction factor coefficient based on the different fittings. So elbow 45 it is 0.35, elbow 90 it is 0.75, T joint it is 1, return band it is 1.5, for coupling it is 0.05, for union it is 0.04, for get valve wide open it is 0.17, for half open this is 4.5, for globe valve wide open it is 6, for half open it is 9.5. So you have the different values of the Kf. Now when you substitute the equation, here it is the final sigma F equal to 4F L by D. This is the loss of, this is the energy loss due to the wall friction or film friction due to the solid surface of the cross section. Then Kex, this is the energy loss, mechanical energy loss due to the sudden expansion, plus Kc, this is the energy loss due to the sudden contraction, plus Kf, which is the energy loss due to the different type of fitting used in the system. So this is the overall energy loss, sigma F. So sigma F can be calculated by using this equation 2.1019. Okay, where the Kf is the loss which is calculated by this table 2.101. So in the table 2.101 you can calculate the different values of the Kf values are given for different type of fittings. So you can refer this table also. Now we will solve some problem. So friction loss and mechanical energy balance. So an elevated storage tank container of water contains the water at 82.2 degrees Celsius as shown in the figure. It is desired to have the discharge rate of at point 2 or is 0.223 feet cube per second. This is the volumetric flow rate at the discharge point. What must be the height of h from the surface of water of tank relative to the exit point. So basically in this problem, this is the diagram given of the system. This is the hydraulic system, and you know the velocity of volumetric flow rate of fluid here. So you need a given amount of fluid from this point. Now in the problem you have to calculate this height. What should be the height of this h, or what is the difference between these 2 points, so that you will get the given amount of water from this point. And here you have the different type of fittings. These three are the 90 degree fittings. You have one sudden contraction also here. Here again, when the water is entering from this tank to this pipe, here again you have the sudden contraction. At this pipe also you have the sudden contraction again. Then you have the different size of pipe here, you have the different size of pipe here. Then you have the friction losses due to the pipe, due to the solid pipe. So you have the friction losses in this problem. You have the losses due to the elbow. This is the 90 degree elbow, this is also 90 degree elbow, this is also 90 degree elbow. You have the friction losses due to the elbow. Again you have the friction losses due to this sudden contraction and this sudden contraction. Now you have to fix the amount of flow of fluid here, and calculate the height h. For that you have to calculate the height h. So amount fluid flowing is given here, that is the 0.223 feet cube per second, and the different k values of kf is given for the different Reynolds number with respect to Reynolds number, okay, in this table. So how to solve this problem? So this is the equation which we have to use for 2 points between point 1 and 2. So between, if you take, this is the point 1 and this is the point 2, you have to calculate this side only, Z1 to Z2. So you have to do the mechanical energy balance between the point 1 and point 2. Okay, so this is the originally, this is the mechanical balance equation. Zg, because the units are in the British units, so you have to use the GC also. Zg by Gc plus V1 square by 2 alpha Gc plus P1 minus P1 divided by rho 1 minus P2 by rho 2 minus Ws equal to Z2 G by Gc plus V2 by 2 alpha Gc plus sigma F. So in this equation, what are the given things? First we have to take the what are the given. So you have to calculate Z1 minus Z2, which you have to calculate. Minus Ws, there is a no pump used in this diagram in this system, so Ws will be 0. So here Ws will be 0. Now comes to the P1 minus P2. Now the point 1 and point 2, this point and this point, both are open in the atmosphere. So these 2 points are the open in the atmosphere, so we can assume that pressure will be same, 1 atmosphere at the both point. So P1 minus P2 will be 0. So in this equation, this term will be 0, this term will be 0. Now come to the this term, this is the V1 square. So what is the value of V1? If you assume that this tank is significantly large, so V1 will be very less. The amount of fluid flowing in at this point at the surface from upper to lower part will be very less if the size of tank is significantly large. So you can assume V1 is 0. So now then you have to calculate Z1 minus Z2, that is the calculation. V2 is given. How V2 is given? Because you have the, you know the cross sectional area of this pipe, you know the flow rate. Flow rate is given here. You have to calculate the H for this flow rate, volumetric flow rate 0.223 feet cube per second. This is the flow rate is given. When flow rate is given and the size of the cross sectional area of the pipe is given, where the cross sectional area of pipe is given? Here. The pipe uses commercial steel pipe schedule 40. So when you know the commercial steel pipe and the schedule number, you can calculate the thickness of the internal cross sectional area of the pipe. So when you calculate the internal cross sectional area of the pipe, you can calculate the linear velocity at the point 2. So V2 is given. Okay, now you have to calculate the sigma F, that is only the unknown quantity in this problem. So here you have the 4-inch pipe and 2-inch pipe. This is the 4-inch pipe and this is the 2-inch pipe. Here it is written, this is the 4-inch pipe, this is the 2-inch pipe. Okay, and schedule number is given. So by using the schedule number and the nominal diameter, this is given the nominal, this is not the internal diameter, this is the nominal diameter. So by using the schedule number and nominal diameter, you have to calculate the internal diameter. So this is the internal diameter. So in exam generally this value are given to you, or the table of schedule numbers are given. In the schedule number tables, you have a column of the internal nominal diameter, then you have the column of the schedule number, and based on that you can choose the, you can determine the internal diameter. Okay, I will explain you in the next class how to calculate the how to use the schedule number charts. Okay, so here, so suppose you know the D1 and D2 based on the schedule number charts, then you can calculate the A3 and A4 by using the pi d square by 4 formula or pi r square formula. This is the cross sectional area of the circular tube, A3 and A4. Now you know the value of diameter of this pipe, diameter of this pipe है ना. So for 4-inch pipe, for large diameter pipe, this is the area. For small diameter pipe, this is the area. Now divide by the volumetric flow rate is fixed because the fluid is non-compressible. So volumetric flow rate will be fixed, Q will be fixed. Q is given as 0.223 meter feet cube per second. Okay, so you can calculate the linear velocity. So linear velocity in this pipe and linear velocity in this pipe. Okay, so here divide the volumetric flow rate to the cross sectional area, you can calculate the linear velocity. In the large pipe, in the 4-inch pipe, it will come 2.523 feet per second. In the small pipe or lower diameter pipe, it will come as 9.57 feet per second. So this is the linear velocities. Now you have to calculate the sigma value. So sigma f, friction losses. So in this system, friction losses are due to the contraction loss at the tank exit. So where the contraction loss? In this diagram, this is the exit of the tank. So here you have a sudden contraction, so there is a loss of energy at this point. Then this is the first loss. Then second is the friction loss in the 4-inch straight pipe. So fluid is flowing from here to here. So due to this flow of fluid, there is this is the solid wall, or due to this solid wall there is a friction. So you have the friction loss due to this 20 feet long pipe. Then third is friction loss in 4-inch elbow. So here fluid is changing its direction from vertical to horizontal. So this is the 4-inch elbow. So in 4-inch elbow you have the friction loss. Then contraction loss from 4-inch to 2-inch. So here the diameter of pipe is changing from 4-inch to 2-inch. So you have the contraction loss in this pipe at this point also. Then next, fifth, friction loss in the 2-inch straight point. So here fluid is flowing from 125 feet here, 10 feet here, then 50 feet here. So this all this straight pipe, you have the friction loss in the 2-inch pipe. So you can calculate directly in one go this value, how much friction is lost, how much energy is losing due to this friction when the fluid is flowing in this long 2-inch pipe. Then the last point is the two elbows. So this is one elbow, this is one elbow. So this is the 90-degree elbows in the 2-inch pipe where fluid is changing the direction from horizontal to vertical, then again vertical to horizontal, and you may have the friction energy loss in this 2-inch in these two elbows. Now you have to calculate all these 6 items one by one. Okay, so we will calculate first contraction loss in the tank exit. So this is the formula which we can use, 0.551 minus A3 by A1. So here value of A1 is very large. Okay, so you can assume this value 0 because in the tank this area is, if you assume your tank is significantly large, then this area is much higher than this cross sectional area. So the ratio of both will be negligible. So you can assume this value 0. Then the equation becomes 0.55. The KEC value becomes 0.55, and when you substitute HC equal to KC V3 by 2, V3 square by 2, you will get the answer. Okay, here you calculate the velocity, you are already calculating, you just substitute all the values, you will get the value of HC, which is 0.054 feet per LB per L. This is the unit of energy in the LBF, fit LBF per LBM. This is the unit of energy per unit mass in the British unit. Then second, you have to calculate the friction loss in the when the fluid flow in the 4-inch pipe. So for that you have to calculate the Reynolds number. Reynolds number equal to dV rho by mu, because it is a circular pipe. So what Reynolds number will come, 2.13193 multiplied 10 to the power 5. This is the Reynolds number. You can see that this is in the turbulent zone, because this is the this is more than 4000. This is in the turbulent zone. And for in the diagram, if value of surface friction factor is given, surface roughness factor is given as 4.6 multiplied 10 to the power minus 5 meter, or this feet. So you can calculate the surface roughness factor, that is psi by d, and it will come 0.000448. This is the surface roughness in meter, and this is the surface roughness factor, which is the psi by d. Okay, d is the diameter. Okay, so it will come 0.000448. This is a dimensionless factor, so you can calculate it in the meter or you can calculate it in the feet. The value will be same. Okay, so now you have to just check the Moody's graph. Okay, Reynolds number is known, value of the friction factor, surface factor is known, roughness factor is known. Now you have to just use the Moody's graph. So where is the Moody's graph? In the MACAP book I will show you in the bigger diagram. This is the Moody's graph. So it is come as a 0.448. So you have to check out the value which is given, nearest value which is given in the diagram. So this line is for 0.0004, this is for 0.0006. so you can use the nearest line, this line, and value of Reynolds number is calculated at as 2.193 multiplied 10 to the power 5. So this is the Reynolds number. So this is the 10 to the power 5, this is the 2 multiplied 10 to the power 5, this is the 3 multiplied 10 to the power 5. So in between here you will get the exact value. Okay, so this line is 0.445, and when you follow this line you will get a point here near to here again, and when you check the y-axis at that point you will get you can calculate the value of f in this curve. So in this way you have to calculate the value of f, or in the problem I will give you the value of f for the different conditions. Okay, instead of going for this calculation you may also get the value of f might be directly given to you. So they have just calculated by using the Moody's graph, and it will come f equal to 0.0047. okay, the length is given in the problem 20 feet. 20 feet is the length. We are calculating the friction loss due to this long pipe. 20 feet is the length. So just substitute the delta L equal to 20. This is the diameter of pipe, that is the 0.3357. This is the f is calculated here 0.0047. V values we have calculated 2.523. Then GC is 32.174. Now just substitute this value here, you will get the friction loss in the film friction loss 0.111 fit lbf by lbm. Okay, this is the friction loss per unit, this is the energy loss per unit weight, per unit pound. Okay, now you have to calculate the friction loss due to the 4-inch elbow. For 4-inch elbow kf is already given 0.75 because it is the turbulent flow. So in the turbulent flow in the table it is given for 90-degree elbow it is 0.75. so it is already given to you. So just use the value, the same value here. Kf equal to 0.75. V is given 2.523 square. GC is 32.174. You can calculate the value of friction loss in the 4-inch elbow. that is 0.074. So where is the 4-inch elbow? 4-inch elbow is this. Here fluid is flowing from vertical to moving from or changing direction from the vertical to horizontal. So this change, due to this change of direction, you have the energy loss, which we have calculated now. Now we will calculate the energy loss due to this contraction from 4-inch to the 2-inch pipe. So here is the contraction loss from 4-inch to the 2-inch. So just calculate the value of A4 and A3, which we have already calculated, 0.02330 and 0.0884. Just substitute the value in this equation. You will get the value of Kc, that is the 0.405, and now you have to substitute the value of 405 in this equation. It will come 0.045 multiplied by downstream velocity. Remember, in the contraction you have to use the downstream velocity, in the expansion you have to use the upstream velocity, in the pipeline you have to use the upstream velocities. Okay, so here the velocity will be 9.57 square divide, this is the velocity 9.57. just substitute the value of Kc here, value of velocity here, this is the Gc. You can calculate the value of Hc due to energy loss, mechanical energy loss due to the contraction. It will come as 0.575. okay, now we have to calculate the friction loss in the 2-inch pipe. So basically the fluid flowing from this point to this point. So due to the friction of solid wall of the pipe, what is the loss? So overall length of the pipe is 125 plus 10 plus 50. This is the overall length of the pipe. So due to this long pipe, how much energy, mechanical energy is converting in the thermal energy? So formula again is 4F delta L by D. 1 minute. 4F delta L by D, V square by 2GC. So delta L equal to 125 plus 10 plus 50, it will come 185. So 180 for long pipe, and if you calculate the friction factor value from the same equation, you will get F equal to 0.0048. So this will come from the Moody's curve. So for that you have to calculate the Reynolds number. Reynolds number value is this. For this is the velocity, this is the diameter of 2-inch pipe, this is the density and viscosity will be the same. You will get Reynolds number 4.28 multiplied by 10 to the power 5. This is the surface, this is the roughness factor, that is the Xi by D, that is equal to roughness, that is 0.0015 divided by diameter 0.1725, it will come 0.00087. Now if you go the original curve here, so this is the 0.4, this is the 0.6, and this is the 0.001. so you can use the this line because this is near to the 0.87. okay, so when you use this line, and this is the 10 to the power 5, 10 to the power, and your Reynolds number is 4 multiplied by 10 to the power 5. So this is the 10 to the power 5, this is the 1 2 3 4. So here you will get the around here, and you, if you check the value of the y-axis, you will get the friction factor value. okay, so it will come 0.0048, or in the exam purpose we will not give you the Moody's chart, we will directly give you the friction factor values. okay, so if you know the friction factor value, you will know, you can just calculate you can substitute the value of delta L equal to 185, D is the diameter, that is equal to the 0.1722 multiplied by 2 multiplied by GC is 32.175. Here it will come V, velocity is 9.57. just substitute all the values, you will get the friction factor, that will come as a 29.4. okay, now you have to use this value. Now this is the, you have calculated the friction energy loss due to the fluid flowing in the 2-inch pipe. Now the last thing is the energy loss due to the two elbows. So where are the two elbows of 2-inch? these are the two elbows. Here fluid is changing its direction from the horizontal to vertical. Again here fluid is changing direction from the vertical to horizontal. Now you have to calculate the energy loss in these 2 points. Okay, now for elbows, as I discuss you, here fluid is turbulent. For turbulent flow in the 90-degree elbow, the coefficient is, the fitting coefficient is 0.75. So just substitute the value of 0.75 as the kf value is 0.75. 2 is multiplied because you have the 2 elbows. है So 2 multiplied by kf multiplied by v square by 2gc. Again make sure this value of gc will come when you have the British unit. When you are using the SI unit, this gc will not come. Okay, so just substitute the all values in this equation. Here v square, the value of v is already, we have calculated the velocity of the fluid. You will get the, this is the kc, this is the gc. You will calculate the HF will come as a 2.136. okay, now the next step is to just add all the values. When you add all the values, it will come, this is the energy loss due to the sudden contraction, this is the energy loss due to the sudden contraction in the tank to 4-inch pipe, this is the energy loss due to the fluid flowing in the 4-inch pipe, this is the energy loss due to the elbow present in the 4-inch pipe, this is the energy loss due to the sudden contraction from 4-inch pipe to the 2-inch pipe, this is the energy loss due to the fluid flowing in the 2-inch pipe, and this is the energy loss due to the 2 elbows present in the 2-inch pipe. So overall energy loss will be this much. You can see in this diagram major energy loss is occurring due to the fluid flowing in the 2-inch pipe. So friction loss due to the solid wall or skin friction is the major loss. That's why we are calling the friction loss due to the skin friction or the friction loss due to the fluid flowing inside the pipe is the major loss. So this is the major loss. So the overall friction loss comes as a 32.35 fit lbf divided by lbm. So this is the per unit mass of friction energy loss. Now as I discussed you before, the pressure at this point and pressure is this point should be equal. Why? This is the open at atmosphere, this is also open at atmosphere. So pressure at this point, pressure at this point will be equal. So P1 minus P2 equal to 0. I already discussed this with you before. And Ws equal to 0 because there is no pump. V1 equal to 0. Why? Because V1 is given as a, V1 is 0. Why V1 is 0? Because the size of the tank is significantly large. So you can assume V1 is 0. Alpha is 1. Why? Because fluid is turbulent. Flow is turbulent. So you have to just substitute the value, all the values here. Here it will come V2 square divided by 2GC. H G by GC equal to V2 square divided by 2GC. Okay. Here alpha will come, alpha equal to 1. When you substitute alpha equal to 1, this is alpha, V2 square by 2GC. Just substitute all the value here plus sigma F. This is the sigma F. Now when you substitute all this value here and calculate, so H comes as a 33.77 fit. So this is the height of the required height of the system. Okay, for maintaining the fluid as a fluid, for maintaining the fluid flow rate 0.223 feet cube per second. Okay, so this is the solution of this problem. Now this is the second problem, similar problem. The difference between this problem and the above problem is that here you also have the pump inside the system. Okay, and now here you have to calculate the power requirement in the pump. Okay, in previous problem you have to calculate the height. Here height is given. In this problem you have to calculate the power requirement of the pump. This is also the similar problem, and here in this diagram you can understand that here you have a tank 1 here and tank 2 is here. This is the 1 point, this is the 2 point, this is the entry point of the system, this is the exit point of the system, and you want to flow the fluid from this tank to the this tank, overhead tank. Okay, the height of the overhead tank is the 15 meters. So difference between the these two elevation difference between these 2 points is the 15 meter. This is the pipe, 4-inch pipe, which is used to flow the fluid. The length of the pipe is the 5 meter plus 50 meter plus 15 meter plus 100 meter. This is the length of the pipe. Then you have the 2 elbows in the pipe, 1 elbow and 2 elbow. So water the friction loss may occur due to the sudden contraction here, first point, then the due to the friction loss in the length of the pipe, that is the 5 plus 50 plus 15 plus 100, then due to the 2 elbows, and then due to the sudden expansion. Okay, so if you are using the, if you substitute all the values in the original equation, you can calculate the value of power requirement of the pump. Okay, this is the same problem, and just you have to follow the same steps. Okay, so you have to calculate the first the sudden contraction. Again here, due to the area of the tank is significantly larger than the area of the pipe, so that's why this term will become the 0 or negligible, and you will get Kc as 0.55. and when you substitute the value in equation, you will get the energy loss due to the sudden contraction. Then you have to calculate the energy loss due to the friction loss in the straight pipe. So when you follow this formula, you can calculate the energy loss. This is the F. F is calculated by using the surface roughness factor and the Reynolds number. When you, then this is the length is 170 meter. If you add 5 plus 50 plus 15 plus 100, it will become 170. So just substitute all the values here, you will get the energy loss in the straight pipe. Then there is a friction loss in the 2 elbows, so just substitute the value here. Kf is 0.75, and elbows, it is a turbulent flow, so Kf should be 0.75, and V square is given in the equation, so you can calculate the value of energy loss in the elbows. Then you have to calculate the energy loss in the shudder extension. So here also V1 is greater than V2. V1 is greater than V2. Okay, why? Because in the original diagram, the diameter of tank 2 is significantly larger than the diameter of the pipe, so you can assume that this ratio A1 by A2 is 0 again, so Kex will come as a 1. So just substitute the value of Kex as a 1, and where substitute the value of V2 here, 0.60. This is the, in the extension you have to use the velocity which is the upstream velocity, so that is equal to 0.6083 divided by 2, where here the GC will not come. You can see here we are using the SI unit, and here we will not dividing the values with the GC. Okay, so here GC should be 1. Actually you can also assume that in the SI unit value of GC will be 1. Okay, so HEX will come, the energy loss due to the extension will come 0.185 joules per kg. Then you have to calculate the overall friction loss, which will become 6.837 joules per kg. Now the velocity difference both point is equal to 0, and the pressure difference between both point equal to 0. Why? If you check this diagram, here also the diameter of the tank is significantly large, here also diameter of the tank is significantly large. So this is the entry point of the system, this is the exit point of the system. So when you are doing the mechanical balance from this point to this point, so the velocity will be 0 here, velocity will be the 0 here. Similarly the pressure drop, so pressure of this point is atmospheric pressure, pressure of this point is also atmospheric pressure, so pressure drop will also, you can assume that pressure drop is 0. Okay, so if the velocity is 0 and pressure drop is 0, then you have to just friction loss equal to the power requirement, because the kinetic energy loss and the that will be 0. So the difference will be due to the friction loss as well as due to the potential energy difference. So here the elevation is 15 meter. So in the original equation, this term will become 0, v2 minus v2 square minus v1 square becomes 0, p2 minus p1 becomes 0. Just check this equation. In this equation, v2 minus v2 square minus v1 square becomes 0, p2 minus p1 becomes 0. Okay, so you have only the three term g, z2 minus z1. So z2 minus z1 is given as a 15. So 15 multiplied by z, 9.8. This is the g, z2 minus z1, which will come as a 15 multiplied by 9.8. Then you have the sigma f. We have just calculated the sigma f here, plus ws. So sigma f equal to this 6.837 multiplied by w plus ws equal to 0. So this is the elevation, 9.8 multiplied by 15 plus sigma f is equal to 6.837 plus ws equal to 0. So when you solve this equation, ws is come minus 153.93. so this is the work done by the pump on the system. Okay, now the flow rate of fluid is given as a, in mass flow rate you can calculate the mass flow rate, which will come the 4.991 kg per second. So now you have to calculate the power requirement. So the unit of this is joules per kg, and the unit of power is joules per second or watt. So you have to calculate the energy requirement in watt or kilowatt. Okay, so for that you need the, what is the flow rate in the mass flow rate of the system. So you know the volumetric flow rate that is given in the system in the problem. Volumetric flow rate 5 multiplied by 10 to the power minus 3. Okay, and liquid is water. Density of water at 20 degrees centigrade is known, that is around 1000 kg per meter square, meter cube. Just divide by the to the kg per meter cube, you will get around 5 kg per second your mass flow rate. So mass flow rate will come, if you assume 998.2, then it will come 4.991 or 5 kg per second. So just multiply this value to the ws, you will get the power. Okay, or if you know the efficiency of the pump, if the pump efficiency is 65%, then divide it by the 0.65. okay, so you will get the power. So what is the value of power? And is 1182 watt or 1.182 kilowatt. So this is the this size of pump. This is the power requirement of pump. Of this size of pump is required to flow the fluid from point 1 to point 2 when the flow rate will be, and the flow rate will be given as 5 multiplied 10 to the power minus 3 meter cube per second. Okay, so my suggestion is you to that I am giving these two problems, this problem and the second problem, both problem as a tutorial to you. You have to solve this problem on, first you understand both problem and try to solve these problems. In next week I am also giving you more problems related to more similar problems where you have to calculate the friction losses as well as the power requirement of pump in the tutorials. Okay, so first solve these two problems, first understand these two problems, then try to solve by your own these two problems. Okay.